Hi, I'm Aaron Packman from Northwestern University, and I'm going to describe the results of a study on the dynamics of arsenic in the rivers of northern Chile. This work's collaborative between Northwestern University in the U.S. and Católica University in Santiago, Chile, and has involved numerous researchers as well as a large number of students from both institutions. The first thing to consider about the Atacama Desert is, of course, that it's very dry, known as the most arid place on Earth. So the location is in the northernmost region of Chile, extending into Peru. And you can see immediately that it's a very harsh landscape, extremely arid, extremely rugged. And these scenes are typical of wide regions of the Atacama where there's really no vegetation and essentially no water. Nonetheless, there are major river systems in the Atacama, and the one we're looking at today is the Rio Loa system. It has this characteristic U shape. It originates in the Andes near the Bolivian and Argentinian borders. And you see from this very nice aerial photograph that it's highly incised in many regions. And you have an extremely arid landscape everywhere except in the river valley, which is often full of vegetation. Now, arsenic in this system results from hydrothermal activity associated with the Puna Altipano volcanic complex. So you see here the main stem of the Rio Loa, and most of the arsenic comes from this tributary, which is the Rio Salado. And the headwaters of the Rio Salado include the El Tatio hydrothermal complex, which is one of the largest ones on Earth, generally regarded as being the third after Yellowstone in the U.S. and Rotorua in New Zealand. So you see here first a satellite photograph of El Tatio with the major drainage channel and several photographs of different hydrothermal features in this system. So you see a number of continual discharges of hydrothermal water leading to the formation of pools and ultimately to runoff channels. And this type of runoff channel is in fact the headwaters of Rio Salado, this major tributary of the Rio Loa system. So you have a direct discharge of arsenic from this one point source immediately at the headwaters that's propagated throughout the river system. So the objectives of our work were to essentially characterize the dynamics of arsenic or arsenic distributions throughout this river system, and we're focusing on a few key features. First, it's waterborne arsenic. Secondly, it's arsenic concentrations in sediments so that we can relate reservoirs of arsenic to mobilization and downstream efflux. And we used a suite of methods. So some were conventional water and sediment sampling with bulk arsenic concentrations. In other cases, we used state-of-the-art and even new methods to improve understanding of the behavior of arsenic in sediments. I should also mention that all of this work was funded collaboratively between the U.S. National Science Foundation and CONICET, which is the Chilean National Science Foundation. So it's truly an international collaboration on a problem of global interest. So I'd like to give an overview of the sampling sites. I have a Google Earth map that shows the exact location of our sampling sites. And you see here again this U-shaped river. And most of our work was actually in Rio Salado, looking at the fate of arsenic from El Tatio down into the Rio Loa system and past major population centers in Calama. And also water supply from this river is used for the city of Antofagasta, which is on the coast out this way. And another feature of interest is that just near Calama here is Chiquicamata, which is the largest open pit mine in the world and is primarily a copper mine. So you can see immediately from the photographs that there's a wide distribution of different types of fluvial features along this river system. So El Tatio is at around 4,200 meters above sea level. The city of Calama is around 2,500 meters above sea level. And of course, the river discharges at the coast. So you have very strong topographic gradients and a great change in the river as you go downstream. So this is the upper Loa system, which has less arsenic, not no arsenic, as we'll see in a minute, but less. And wherever the river valley opens up, you have extensive vegetation. From El Tatio, it drains into the Rio Salado, which is essentially barren, very steep, very cobbly, canyons surrounding it, and no vegetation. But as you go downstream, you do eventually find the same vegetated features to the confluence. And there are a few locations where you have man-made reservoirs with extensive storage of water and sediments. So the first thing we looked at is patterns of arsenic in transport along the Rio Loa system. And we found something fairly surprising, which is that arsenic behaves essentially conservatively. So in the upper Rio Salado, you see strong decreases in concentration downstream from El Tatio. This is because of dilution from tributaries that bring in much less arsenic. However, after you have this region of a lot of tributaries, you see this increase in arsenic concentration consistently downstream, which is almost certainly attributable to simply evaporation in this extremely arid environment. And this conclusion is reinforced by this graph, which compares the behavior of arsenic to boron. So boron also comes from the hydrothermal systems. It is well known as essentially a conservative substance, and you see that arsenic follows boron very strongly, showing the behavior of arsenic is largely conservative as well. Finally, down here we have a dendrogram that compares the relative behavior of different elements of interest. And again, you see arsenic associated with elements that normally behave conservatively and less associated with substances that we normally think control arsenic behavior, such as iron. So even the bulk chemistry suggests a difference in the behavior of arsenic in this system. Now we're switching to sediment results, and I have here first the upstream sites along Rio Salado. There's a small reservoir to supply water for the mining operation. That's the Codelco reservoir. And you see you have extremely high arsenic concentrations here, above 1 gram per kilogram in the sediments. And you find distinct layers where there's arsenic, and it's not particularly associated with either iron or manganese in those layers. There is a location somewhat further downstream where we do find a strong connection between arsenic concentrations in both manganese and iron. And this is a location where you observe local precipitation of iron deposits in the stream bed. And so it's clear that there are some local processes that can scavenge arsenic from the system. Right, here's the rest of the sites, and I've put them on the map here so you can identify the features. So this set is the upper Loa, and you see there are generally low arsenic concentrations, but there are some places here where there are some significant arsenic concentrations. Further downstream, you see a wide variety of behavior. Generally, you have arsenic here that you can see is enriched towards the surface, but in the major depositional basin in Sloman Reservoir, you see an unusual pattern of very high arsenic concentrations at depth related to manganese and essentially inversely related to iron. So there's a defined layer here where there's a lot of arsenic, and again, it's not necessarily an association with things we would think it could be. And so this could either be from diagenetic processes in the sediments, or in my opinion, more likely that there was a unique event or a time series of events that led to the formation of this particular layer, which could be a large flood, which occur in this region but very infrequently, or potentially something in terms of mining practices historically that led to the release of material with this particular composition. Another unusual feature that we observed is in the sediments, arsenic is highly correlated with calcium. And I show here results from multiple places along the river system, and you see this very consistent relationship. And you'll find that the R factors for these correlations are all over 0.9. So arsenic is very strongly correlated with calcium in the sediments. And this could be from potential scavenging by calcium phases, potentially calcium carbonate phases, which again would be highly unusual for arsenic. Now, we use some advanced methods. In fact, this is a new method, never before applied to arsenic, in order to assess the behavior in the sediment. So I'm going to describe this briefly. Recently, we've been developing tools for X-ray difference micro-tomography to assess distributions of particular elements within sediments. This is a synchrotron-based method where you take a small core, you subject it to synchrotron X-ray beam, and obtain a series of images of absorption of X-rays in the sample that you can then rotate and reconstruct into a three-dimensional tomogram. That's shown here. So you get very nice pictures. You can also identify subpopulations of individual elements. This one's for zirconium, and it's illustrated here, where you have a transition in X-ray absorption at unique energies for each element. And by taking these maps of absorption above and below this zirconium edge, for absorption edge for arsenic, you can then isolate that element within the sample. And the red here is, in fact, colloidal zirconia deposits. So these methods have been developed in the last few years. Well, we applied this to arsenic, and this is the first presentation of any results of tomography applied to assess arsenic distributions in sediments. So this is actual data on the arsenic edge that we use. So again, we take two images above and below where you get a contrast. The difference between those shows uniquely the distribution of arsenic. So here are a couple of examples from different locations. The one on the left is from the El Tatio, where you're forming these geyser center deposits. And you see right away some unusual behavior that in this sample, the arsenic is concentrated and not uniformly distributed with the center sample. So there's either a process that concentrates arsenic within the mineral, or arsenic could be precipitating into some particulate phase, which is then incorporated into the center matrix. Conversely, downstream in the Rio Salado, we find that there are background sediments. We see these grains here that essentially don't contain arsenic. And the arsenic is present in colloidal phases and potentially coatings. Now, this is the location where we observed a lot of iron precipitation. So we find iron in a fine colloidal phase near the surface, as well as depositing within the pore space made by these background grains. So this method really gives you detailed information on the spatial distribution of solid phase arsenic within soil or sediment samples. In addition, we used X-ray absorption spectroscopy, which is another synchrotron-based method, to assess the speciation of arsenic, and these results are from the El Tatio site. So first of all, we observed precipitation of arsenic specifically in microbial mats. You see a peak for arsenic here. Actually, this is from scanning electron microscopy results. The speciation is shown here on the right, and using, again, this X-ray interaction with elements of interest, you can observe the spectra and observe either the X-ray absorption near structure or fine structure, which is this region of the spectrum, and evaluate the elements that arsenic is associated with and speciation of arsenic in the sediment. And this analysis showed that arsenic that's incorporated into the microbial mats and in the center materials is an oxidized arsenate type mineral, specifically an iron arsenate type mineral, which might not have been expected given that it's a hydrothermal source. So to sum up, I would like to have both some conclusions of what we learned so far, and there are definitely a number of unanswered questions here that we're continuing to pursue. So the main conclusion we have on the behavior of arsenic in low flow conditions in Rio Loa is that it's behaving relatively conservatively. In this unusual river system with unusual chemistry, you have arsenic associated with elements like boron that are highly mobile. So in general, we see flushing through the system, and dilution and evaporation controls the behavior of arsenic. However, we also know there is retention within the river system, and this has been known because there have been some disasters previously where these rare flood events in the Atacama have led to the downstream propagation of flood waves containing very high concentrations of arsenic. So there's an open question as to the major mechanisms of arsenic retention and remobilization in this system. And we think that this is not the kind of chemistry we would find in the U.S., in most regions of the U.S. anyway, that are more human environments. And that arsenic may not generally be controlled by iron, oxide, hydroxide minerals in the river system. Instead, we're looking at things like evaporite minerals, which form plentifully throughout the river system and in the floodplains. In addition, we did observe that local processes can be very important in scavenging arsenic. And we use these advanced methods, synchrotron-based methods, to understand both the distribution of arsenic, the structure in relation to sediments, and the speciation. And we think these methods potentially can be used very, very widely to improve understanding of arsenic dynamics in freshwater systems. All right, thanks very much, and I'd be happy to answer any questions.
We have a few minutes for questions, please.
Do you anticipate a role for phosphorus in some of the downstream reservoir sediments? Is that what the evaporation thing might be?
This environment is very unusual. You actually form a lot of chloride minerals. Calcium chloride minerals are well known in this system. So you could have very unusual mineral phases that you can accumulate arsenic. And my best guess right now is you have a lot of accumulation in the floodplain or kind of riparian areas where you could evaporate minerals containing arsenic that would be readily mobilized whenever you have a flushing event. Within the fluvial sediments, it seems like calcium phases, I guess it could be calcium phosphate, calcium carbonates, could contain a lot of arsenic. My colleagues who are more geochemists are exploring those issues.
One more question? Well, thank you. Next speaker is Wendell Ila from Arizona, and he'll tell us something about the experimental results.
Okay, thank you. What I want to talk about today is, as Rudy said, is experimental results, but with the caveat that they are very strongly analogous to what we see in natural systems. So I'm going to talk about engineered systems and then try to show how that is really tied in with exactly the same sort of processes that operate in natural systems. And what we learn from one, we can certainly move over into the other. The context here is that arsenic exposure, in terms of human exposure, is really a function of its availability in water. Our exposure is either through direct drinking water contact or through foods that are grown in tainted waters, arsenic-tainted waters. And so what we're really interested in is determining to what degree arsenic becomes mobilized in an aqueous phase as opposed to staying on a solid phase. The two types of solid phases we see arsenic in or associated with is either as an adsorbent or on an adsorbent phase or as part of a mineral matrix. And so we predominantly see these in different redox situations, though. So we tend to see the sorbent phases in the oxic, anoxic zone where nitrate or above in the electrochemical chain exist. And we tend to see the crystal phases when we are down in the highly reducing areas where sulfides and that sort of thing are present. Now, this is not to say that we don't have oxic mineral phases, scorodite, those sort of things. But the real mobilization comes out generally from the sorb phases. That bringing up this whole issue of redox chemistry, which I'm sure will resonate through all the talks today and is already resonating. And that is that it's really the redox chemistry that liberates the arsenic or determines its mobility. And so if you're in an oxic environment initially and arsenic is stable in that oxic environment, if you go anoxic or reducing, you tend to see mobilization. Vice versa, if you're in a reduced phase and you then make it oxidizing, then you'll again see mobilization out of it. And so what I'm going to really talk about, though, is this oxic, where it's initially an oxic phase, and then it goes through a reducing environment, and you see the mobilization through that transition. It's not to say that that's the only transition that would liberate arsenic. If we're talking in the oxic phases, we're really talking again about the sorbed arsenic, and so we're thinking about things like iron, manganese, calcium, as the previous speaker said, those sort of things that are really holding up the arsenic in the oxic environment. From an engineered perspective, if we have arsenic in water and we want to remove the arsenic, iron is by far the predominant sorbent that's used. We use it essentially just pass the arsenic-laden water over an iron-based sorbent. The arsenic comes out, sorbs to the iron, and you go ahead and deliver the potable water or the cleaned water at that point. The issue here then, really from my perspective, is how do we keep the arsenic on that solid phase? because obviously arsenic's conservative. We get it out of the water, where the whole point at that time is, can we keep it on the solid phase and not have it re-released, re-enter the environment? And this brings up this whole issue of the transitions from the oxic phase down into an anoxic regime. This is a graph I got from Peggy O'Day, used it several years ago in a presentation. I like it a lot. It really just illustrates these associations between iron as an indicative of these of the primary metal oxide that associates with arsenic in this oxic environment. And you can see that what it's suggesting is that you have the oxidized iron, iron 3, associating with arsenate, arsenic 5, and that's as a sorption process, so there's an equilibrium set up there. But then if you present organic matter, create a reducing environment, then the arsenic 5 can get reduced to arsenic 3, as well as the iron 3 can get reduced to iron 2. And so you have both of these processes going on simultaneously. The conventional wisdom in these sort of systems where we see release of arsenic from these iron minerals under reducing conditions, the conventional idea has been, we've said, well, that's reductive dissolution of the iron sorbent, and that's releasing the arsenic out. And that's kind of been the mantra that's gone along for quite a few years. I want to suggest that perhaps that has a flaw in it. And the following data I'll show you is really going to that point largely. And to suggest really that that reduction of the iron, in fact, keeps the arsenic more immobilized than would otherwise happen if there were not the iron present, that is a redox-sensitive species on it. So we'll go there on it. But the context that I look at this from is that the way we entered this field, and this goes back quite a few years now, was we were interested in how water treatment residuals, sorbents, iron sorbents that are placed in landfills, how do they retain the arsenic that's sorbed onto those? And so the initial work we did, we essentially said, well, let's just set up a landfill in a laboratory and see how the arsenic is released from those iron sorbents if they're placed in this simulated landfill. And that's really what this column is showing. And so all we did is just set up a little simulated landfill in a 6-inch sewer pipe and started running water through it. So real rocket science. And what we saw, though, was that at the or the least resolution level, if we just look at total iron and total arsenic, all of the arsenic went in as arsenate. It was sorbed onto an iron sorbent, commercial sorbent. And if we look at the release of those two species, just total arsenic and total iron, so we're not speciation, not particle versus dissolved fractions, just the total of each of these, what you see is initially the over in this range, you'll see the arsenic. This is the arsenic trace to red. This is the iron trace to blue. You'll see that they track each other pretty well. As the iron goes up, the arsenic goes up. This is in the mobile phase coming out in the effluent. And then as the iron starts dropping down, the arsenic drops down. But you see in this region here, there becomes a decoupling. And what happens now is your iron continues to decay away, but your arsenic rises up. So there's this decoupling of the iron from the arsenic system on it. If we look then at the original ratios, so this line here is the original arsenic to iron ratio of what went into the simulated landfill. And then this is the ratio of the arsenic to iron that's coming out. What you see is initially the arsenic to iron ratio is much lower than what went in. In other words, we're leaching out more iron than we are arsenic in a relative proportions. What happens though is out here at this point where the arsenic, we saw that arsenic decoupling, we see that ratio, as you would expect, rise precipitously. In other words, the iron is no longer coming out of the column at the rate, but the arsenic is coming out at a much faster rate. 2 points to make here. The first one is that this decoupling apparently happens relatively late. And secondly, that the decoupling is both for the particular phase, which is the open squares here, and for the dissolved colloidal phase, which are the filled solids here. And they're actually right on top of each other. So it's not as if you're sloughing off material that has the initial ratio on it, but you're actually, even the particles that are coming out are being generated with this new ratio of iron to arsenic on them. So these aren't just parent fragments coming out of the column. These are actually a solid that has this new ratio that's seemingly to some degree in equilibrium with the new aqueous phase ratio of iron to arsenic. That motivated us into a number of other studies, and I'm just going to fly through here at the 50,000 foot level on a couple of these. What we did then was we stepped back and simplified the system considerably. So instead of trying to create a whole landfill, what we did was we said, well, we're going to have a very simplified system in which we have a single electron donor, that being lactate. So we feed the column just with lactate. We also only add the iron arsenate in with no other compost, paper, all the other things that go into a landfill. And so we have this AFH, amorphous ferric hydroxide, ferrihydrite, if you will, precipitate that has the arsenic on it. We mix that with glass beads, and then we just feed it in an upflow direction now with this lactate influent material on it. So very, very simple system on it. And what we see then is that the first point is that you get this same behavior early on. Now this is just the arsenic trace. There's no iron in this trace. So we're looking at the arsenic speciation, total plus speciation. We get this very long lag initially where there's very little arsenic coming out of these columns on it. Then there's this very, very rapid rise in arsenic. You'll note that this is almost all arsenic 3. All of the arsenic goes in as 5, so the arsenic's coming out as reduced arsenic. It's gone through that transformation. The arsenic 5 is very low. It spikes up here and then drops off precipitously on it. So the points here being, first of all, to gather is that we have very high arsenic released. About 65% of the arsenic has gone out of that column over this approximately 9-month period. There's this lag that starts out before you start getting arsenic coming out. You get this high peak that doesn't persist for a long period. And from an engineering perspective or environmental engineering perspective, we're way above the hazardous limit on this. This is 5 ppm as the toxicity characteristic on it, so we're way above that. If you look at the iron trace relative to that arsenic trace, what you see is the iron essentially is bouncing around, but is pretty steady over that whole period on it. So you're not seeing the phase or the elution of the iron that matches the elution of the arsenic on it. The other piece here is that we only lose about 5% of the iron out of this column, where about 65% of the arsenic came out of the column on it. Another interesting point is that if you remember where that peak was, what we see, and this is looking at the lactate influent versus what's coming out in the effluent. Initially, the lactate is getting oxidized to acetate, but the acetate is persisting in the column. So there's that single event going on in terms of microbial activity. What we see is right at that point where we have the peak, the acetate starts getting utilized, suggesting that there's another microbial population, a different type of microbial population coming into play on it. The other piece of evidence here is if you look at the column over time, you see a tremendous difference in terms of the coloration of the column, where you start seeing black blotches in the column, which we can, and I won't show you the data on that, but essentially is magnetite being formed in this column as a function of time. So it goes in as ferrihydrite, and now we're seeing magnetite starting to be formed in that column. And this is relatively quick on it, day 21. So this is early on in the piece on it. And I'll skip this, run out of time very quickly here. But the idea being that we do XRDs on this. We can see the magnetite. We also see goethite. If we change the rate of flow through that column, we can have a propensity toward goethite as opposed to magnetite. And what I want to show to finish this up is this idea that if we have a non-redox sensitive media, so we have a zirconium or a titanium or a lanthanum oxide as opposed to an iron oxide, that what we see is we see a very much higher elution of arsenic out of those columns that don't have the iron involved in them on it. And let me go to this one. That's where your 5 ppb or 5 ppm is. And I'll show you on this. The idea being here, if we look at these 3 different media, here's the iron that we baseline against, lanthanum, zirconium, titanium. You look at the percent of arsenic lost versus percent of media lost, in other words, whether it's iron or zirconium or titanium. All of those, they don't come out in the ratio they went in at. You're getting a lot more arsenic out than you're getting media out. But what you see is that the percentage of arsenic lost in the iron column is about 15%, where you're up at about over double that in the zirconium and titanium columns, which are the 2 columns that lose less media. In other words, the reduction of the iron in these columns is not leading to an enhancement of the arsenic release, but in fact, what we believe at this point is that it is helping to retain the arsenic, and that's through a reprecipitation of the magnetite and other reduced mixed iron species that now are sequestering the arsenic, and in fact, tending to keep it within the system as opposed to allowing it to go ahead and come out in the aqueous mobile phase. With that, I'll finish up and take any questions that you might have.
We're running a little bit out of time, but let's take one question.
Yes, we're actually involved in that right now. John Chorover, Dr. Chorover at the University of Arizona, we're working with him on that. That's something we're really interested in, and we have a number of columns of these columns we're doing autopsies on, different stages with different amendments, and looking at that. I think it's the way to go. Yep.
Thank you. Next talk is given by Weinman, Goldberg, Savage, Zhang, and several others. And it's on the coevolution of Asian aquifers and arsenic, how understanding sedimentary history can help predict patterns of arsenic heterogeneity.
Is that the laser? That's the microphone. The laser's right here. How do I put this on? Here, you want one? And then click this. Okay. Speak into this one. Oh, now that you're wearing that, you're fine. And sorry, Vance, just use the mouse.
Okay. Hello, everyone. Today I'm going to talk about some work that we've been doing on the coevolution of arsenic in aquifers and arsenic, and understanding how sedimentary history can help predict patterns of arsenic heterogeneity. So a lot of the regions of the world that have arsenic problems are very heterogeneous in the arsenic distribution, and I'm trying to understand how aquifer formation can impact that heterogeneity. So this is just a quick slide. It might be a little cut off. I can't quite see from here. But to why we care about arsenic, or some history on arsenic. So back in the 1970s, a bunch of donor agencies emplaced 2 wells into Bangladesh. And in doing so, they inadvertently exposed many people, millions of people, to arsenic in drinking water. Oh, sorry. Arsenic in drinking water is not the only way that we can be exposed. There was a recent meteor impact about a year ago in Peru, and they also have arsenic in the groundwater, and the arsenic is shallow enough that a lot of it volatilized, and residents in nearby villages got ill just from smelling or breathing in the arsenic. Also, industrialization requires good quality water, so a lot of the developing regions of Asia, they're developing at phenomenal rates. They need good quality water. There are also a lot of health and social impacts, so people with arsenicosis are shunned, and some new work shows that there are babies that are prenatally exposed to arsenic. They have lower IQ scores, so it's a problem. In addition, there are agricultural impacts. We have no idea what impact fertilizers or irrigative pumping is doing to the aquifer arsenic. And in addition, Asia is a huge exporter of a lot of our food, so there are a lot of questions about what's going on with the arsenic. In addition, a lot of, again, this area is rapidly developing. A lot of the cities are developing very fast, and in doing so, they're not keeping up with the unsewered water. So that's what happened in the Hat Yai Basin in Thailand. So they had a plug of reductants that went into the aquifer, and they released arsenic. So it's a problem, again. And last, well, we're innovative species. We can deal with arsenic in the water. What's the big deal? Well, a lot of the mitigative strategies are not going checked. So when we were in Nepal, there were people who were using their filters as egg baskets. And in New Jersey, people who didn't have their filtration units in the proper order were accidentally releasing spikes of arsenic out by growing arsenic bacteria. So this is a problem. So this is a summary slide. Why is arsenic so dangerous? Long-term exposure can cause a variety of diseases. It's carcinogenic at very low concentrations. It's hard to detect. World Health Organization guideline is provisional, meaning that it's probably going to go down as our detection limits get better. So this number will probably go down. In addition, well, as I just showed, it impacts a variety of sectors. World Bank estimates that more than 60 million Asians are at risk, and each year new groundwater incidents are being reported in other countries. This is a map of commonly affected countries with high groundwater arsenic. This is a World Bank map, and there are also, like I said, new countries being reported every year. So I get Google reports every morning of more and more places affected with arsenic. So there are a lot more uncommon places with arsenic. But I just wanted to show you how heterogeneous, how widespread arsenic is on Earth. So these are the places that arsenic is more common, and you can see in the Hetio Basin, Inner Mongolia, over very small spatial scales, tens of kilometers, arsenic is very heterogeneous. This is also a problem in locating clean water. In the Hungarian plain, so blue is clean, the reds are more contaminated. Over very small distances, kilometers, arsenic is heterogeneous. So over 1 kilometer, you have this heterogeneity of arsenic. In the US, Michigan, this spatial heterogeneity, tens of kilometers. In South America, the Pampean Plain, you have, again, tens of kilometers heterogeneity of arsenic. In Africa, you have kilometers, 1 kilometer, spatial heterogeneity of arsenic. In Taiwan, also where they have Blackfoot's disease, you have a similar spatial pattern. Well, why is this? My study area is more in Asia right now. I'm trying to understand why the Asian aquifers are very heterogeneous, and so I wanted to show you, like the world, Asia is very heterogeneous in arsenic. So this is Bangladesh. This is the regional heterogeneity. If you zoom into an area by Dhaka, so this is Ara Hazar, it's just a little bit south of Dhaka, over 1 kilometer distances, over hundreds of meters, wells are very spatially heterogeneous. So wells right next to each other, 100 meters apart, drilled to the same depth, have drastically different concentrations of arsenic. And why is that? The same is true in Vietnam. So this is Hanoi. So here's this regional gradient, this tens of kilometers, low arsenic to high arsenic by Hanoi. And if you zoom in to this one river bend, where here they have it as 300 ppb, if you zoom in this river bend, it's actually much more complex. So this whole river bend is not just 300 ppb. Wells a couple meters apart from one another, they have different concentrations of arsenic. So why is that? In Vietnam, that river bend that I was just showing you, we did some sampling and some sediment studies, and it shows that these aquifer sands are totally different. They have different depositional histories. So the aquifer sands up in the north are Pleistocene, and the aquifer sands down in the south are Holocene. And you can see depositional ages are here. So we did OSL age dating, and we have a 17,000-year-old aquifer age up in the north where it's very low arsenic, and about 700. So 10,000 years of difference between the north and the south. So these aquifer sands are not the same. And this is from the Pleistocene area. So we drilled down 25 meters all the way down through all these muds, and right here we hit orange sand. So these are the sands. This is the aquifer that they're drinking from, and this is a zoom in of it. So this unconformity right here, this is their aquifer. And this is Pleistocene versus in the south, 13 meters. We hit sand. We thought that there'd be lower arsenic here. We thought that there was some relation with the depth of the aquifer unit, but actually these sands, we go down even 36 meters, we don't hit that pebbly unconformity. We're still in Holocene sand. So this region of this tiny river bend, they're using totally different aquifers. In Parasai, Nepal, there's also spatial gradients of arsenic. So this is about 1 kilometer across, going from low arsenic to high arsenic. And in doing, again, sediment studies, there's this age trend of aquifer sand. So the low arsenic aquifer is, again, Pleistocene. It's older than the much higher arsenic, newer deposits here to the east. So why do different deposits have different concentrations of arsenic? So this is something that I'm currently working on. And some of the work I'm doing now is kind of inspired by a paper by White and Brantley back in 2003, where they were looking at different weathering rates of different aged granite. And so in the same fashion that they saw granites that were much older leaching different rates, so they're weathering much less than newer granites, I thought maybe newer deposits had much more labile. They're much younger. They can release more arsenic than older deposits that have been more flushed. So some kind of fluvial signal or sign or impact on the aquifer. And when I did some weathering studies, I found something, well, I didn't get the results I expected. Basically, I thought that these solid lines are older, so the solid lines I expected to be much lower than the dotted lines, so the deposits from the dotted lines are much younger. And I didn't see the expected trend, so it seemed like the weathering of the aquifer sands wasn't quite controlling the same way White and Brantley could infer in their study. And also, I was really more perplexed with, well, I was mad when I got this graph. The arsenic leaching from aquifer sands, the oldest sand actually leached the most arsenic. And, you know, like, I didn't know what to make of this, so I turned to my advisor, and we kind of came up with some other things that we could possibly do. Well, are they the same sands? This seems to be like this resounding question. Well, we took the sand. So there's this sand here from Nepal, 3,000 years old. So it's a much more recent deposit that's a little bit shallower than the deposits that I was looking at before. So the main aquifer itself is a different deposit. But if you look at this sand layer, 3,000 years old, has very low arsenic. And this is what I expected to see much higher arsenic in this 3,000-year-old sand. And this 18,000-year-old deposit here had 400 microgram per liter arsenic, and I thought I'd see something different. If you look at the zircon and the titanite ages in those sediments, they're totally different. So they're coming from different source terrains. If you look at, well, I know this gets a little confusing, but bear with me. I promise to explain this better one day. This area right here, 3,000 years ago, that is the green triangles, and the green triangles that were deposited more recently are actually coming from India, like something like Indian continent, billion-year-old continental crust. So something much older than this 18,000-year-old deposit. It's actually dating to about 50 million years ago. That's the uplift of the Himalayas. So different source terrains signaled in the aquifer sands. And this is a little bit different than what's published. I like this paper by Beebe a lot, so well, he's a good author. But like from this graph, the scientific community kind of inferred that there's no difference in sediment, in aquifer sediment. So the REE patterns with depth in a core are all the same. So from that they infer, you know, there's really no source signal, there's really no source impact from the Himalayas versus the Indian continent. There's really no difference in these aquifers, and we're kind of seeing something a little bit different. Oh, I have time to talk about this. So I have trouble talking about this one too. But the main point for this one is that even though these two areas had the opposite response of what we hypothesized, that their source terrain age is predicted in their leaching. So the older crust is leaching much slower than newer crust. Okay. And I wanted to show again, like these are just quartz sands from a bunch of different sites. More work is being done on this. But the main point of this is, do these quartz look the same? No. They look very different. So the quartz, this cathodoluminescence of different quartz grains. Here's the middle two are Bangladesh. This is a shallower. I think this is like 40 feet, and this one I think is 90 feet. In the same core, you see some yellow catholuminescing grains. These quartz are totally different than these. These don't have any yellow. So the chemistry, the geochemistry of these quartz are different, probably different source trade. More work needs to be done on this, but it's kind of fascinating. So all in all, in the regions I've studied so far, Bangladesh, Vietnam, Nepal, and hopefully one day the US, patterns of arsenic distributions correlate to depositional age trends of the aquifer sediment. So we see again and again these age trends. But in the lab, I'm not able to kind of show that these depositional ages correlate to the arsenic concentration. So in the field they do, but not quite in the lab. So it seems, though, that there's an initial difference of a labile pool of arsenic controlling the different, perhaps, arsenic geochemistries, and younger sediments from the aquifers that weathered more slowly from older source terrains indicate there's this possible pre-deposit impact on the arsenic distributions. So in other words, I think that there is a deep time component on understanding these arsenic distributions, and understanding crustal processes I think also are important for understanding how these aquifers form and predicting how we can possibly, as people, modify arsenic distributions. Oh, that's it. Thank you, everyone. I'll take some questions. Easy questions.
A minute or two.
My advisor doesn't want to grill me? Yes. In which setting are you referring? Yeah, no, that's a great question. And just like I think the previous work was showing, like filtration, like we have like these flow-through tubes, so it modifies somehow, I think, the arsenic, and that's what we're kind of looking at now. So if we perturb the water table south of Hanoi and there's more irrigative pumping and flow is reversed towards Hanoi, will those Pleistocene sands be kind of some kind of adsorbent for the arsenic, or will it not? How far away does something interact? It's a really good question. Anything else? Thank you.
We're moving on, and the next presentation is on hydrogeochemistry and sulfur isotope of high arsenic groundwater of Datong Basin in China. The presentation will be given by Alice, right?
So as I figure out how to get that in. Is that all right?
Yeah.
Okay.
Put it in the pot.
Okay. Thank you. I would just like to quickly add here that I'm giving the talk, but it really should have been given by Jie Jinjun, who was a student of Yanjing Wang at China University of Geosciences that spent 6 months at UT El Paso with me. The idea then was he really came to look at chromium isotopes and selenium isotopes to try and get a better handle on the redox changes that might be occurring in Datong Basin. But before we did that, we did want to get a simple base study to really get a good idea of the general geology or general geochemistry that might control arsenic mobilization. And so that's what I'll be presenting here for him. Do I have the wrong mouse? Okay, I'll just use that. That's fine. Okay. So the objectives were, as I mentioned, to get a better idea of the redox controls on arsenic mobilization. We wanted to just get started by examining the traditional models. We've heard quite a bit of it already today, looking at the potential for iron hydroxide sequestration or the usual sorption, desorption, reductive dissolution, mobilizing arsenic, etc. Examine a little bit the relationship between sulfur and the arsenic cycle. Okay, and then finally try and put them all together and try and get a better handle of the iron, arsenic, sulfur system. We decided to use arsenic speciation. We had samples analyzed at the Illinois Waste Management and Research Center in Champaign, Illinois. They use an HPLC, ICP-MS method to get at arsenic 5, 3, and the organic forms, DMMA and MMA. We use general geochemistry. We still don't have a very good idea of the hydrology, so we wanted to get some idea of the flow paths and general weathering patterns in that particular basin. We looked at a bunch of, I'm going to have to go over your head here, a bunch of other redox species, sulfate, iron, nitrate, uranium, Mn, and molybdenum. And then we did sulfur isotopes of the dissolved sulfate. I did goof up a little bit here. I wish I had gotten oxygen isotopes also of the sulfate. Might have given us a better idea. So there'll be plenty of arm waving as I move along. And those were done at the University of Arizona with Chris Easto. Okay, it's working now. So, okay, I can barely see the other end from here, but just to give you a better idea of where Datong Basin is, we just saw in the earlier talk Hetao in the Inner Mongolia region. So this is between that and Beijing. I think that box should be in the right place. The things have been moving between Office 2007 and 2003, so I think that's in the right place, but I could be wrong. So it's a Cenozoic basin. It's the actual arsenic contaminated aquifer is a young quaternary aquifer. It is in the Shanxi Rift system. We're calling it a semi-closed basin, and I'll show you in the next slide. It's not a closed basin, it's just slow groundwater flow, so we're arbitrarily calling it a semi-closed basin. It is relatively dry, certainly not as dry as the Atacama, but still dry. Arsenic, in the past, there have been reports as high as 1,800. I think that should be micrograms per liter. It's similar to other basins in the region. Okay, the Huhot, we just saw the Hetao in the earlier talk. But all in all, we really don't have much information on this site yet. So, but hopefully with the Yanjing Wan's group working on there, we might get to see a little bit more. We had groundwater samples and spring samples from this particular region. Give you a better idea, we really wanted to get a transect across in both directions, and didn't quite work out, so we will have more upstream data in the future, but right now, that's our highest arsenic. I was really hoping for a cross-section so we get a better idea of mountain front recharge. Okay, so the idea was to get some idea of what's happening as we have groundwater flow from the sites. Don't go by the rivers on there. It's a very dry area. So you'd have to imagine that they don't really exist. For the most part, that would be true. Okay, so that is Jie there, one of his sampling trips, but that's how dry it actually is. There's some of the effects of arsenic groundwater there. That's their only source, pretty much. There have been a couple of deaths also reported in one of those regions. The reason I put this up here is actually for the same reason that we heard the earlier talk, where I think the sedimentary cores will really give us the best information. That will hold the key to the arsenic distribution in the area. The groundwater will tell us so much, but ultimately we'll have to go back and look at the actual sediments and see how variable that might be and where the arsenic might actually be. Okay, so a little bit about the hydrology here. There isn't much seasonal change. This is the piezometric surfaces between different seasons. So most of the water is coming from the sides up there, and it's going down that way. And we aren't seeing much change. So it's mountain front recharge, relatively slow flow, minimal variation between seasons. What we still don't have, remember, we only have data from two ends coming into the center and then going down, but we really need more of the upstream end. There is another student of Yanqing Wang has done a lot of work with water and strontium isotopes, and hopefully we'll see some of that data coming soon, and then we'll get a much better idea of what's actually happening. I'm not sure where my legend is gone, but the blue circles, and I'm going to keep this consistently through all the other slides, the blue circles here are the eastern samples. Okay? The pink boxes are the actual central basin area, and then the blue diamonds are the western margins. Generally, just looking at the general water, definitely what's on the eastern margin is more typical of carbonate weathering, so there seems to be a carbonate dominance there, while the others appear to be more salt, more sodium, etc. I'm not going to go into too much details here for time. Continuing with the general geochemistry, because we don't have a good handle on on the geology yet, I just want to look at it and see where the waters might be and what's actually happening. So here again, the symbols are the same. So the pink boxes are the main basin, and then the others are the two margins. As long as you remember that, I think we'll be okay through the next few minutes. So in general, we're seeing an excess sodium. So it's not all salt. There's got to be some silicate weathering potentially that contributes to the sodium. And that sodium versus chloride there. We have magnesium over sodium versus calcium over sodium on that axis, giving us some idea of what this might be. Actually, I should probably go back. This one sample is geographically a little away. It's that one right up front there. Because of the rivers, I think we got a little bit confused, but really that really shouldn't, it should be part of the same flow. But until we get a better idea of the geology, of the hydrogeology, we've decided to isolate it for the moment, and it does seem to plot somewhere else apart from the main basin region. But in general, so we generally have high Mg calcium ratios, generally carbonate, so it seems to be consistent. So we're seeing some mixing trend between what's on the east flank. What's in the basin and what's on the western margin doesn't seem to be all that different from what we've been seeing. Okay, the strontium over sodium versus calcium over sodium seems to tell us, again, the same kind of story. Okay. So getting to the real issues now. So just to summarize the arsenic data, the concentrations range from around 68 to 660 micrograms per liter in the basin itself. Okay, where the highest arsenic is the most upgradient well. And on the margins, on either side of the margins, it's between 3 and 44 micrograms per liter. The margins are relatively oxidized. Okay, the basin itself, it has high TOC. I don't have that data here, but it's relatively high TOC. It is reducing. What this diagram shows us here, and I probably should have had the axis switch as I should have for all the other plots coming up. But in general, okay, the more reducing waters have the higher arsenic, and of course, they have the higher arsenic 3 as what we would expect. So in some ways, it does support the reductive dissolution mechanism for arsenic mobilization, though that's not entirely clear, and I'll talk about that some more as we move along. So, but in general, in the basin, we have relatively reducing waters, high arsenic. There was one exception there, and they're generally arsenic 3. And of course, we have low sulfate uranium and molybdenum. And then, of course, we see a similar situation there again with one exception. This was not all the same sample, by the way. We seem to have one exception for different parameters with different samples. So it's not one bad sample that, for whatever reason, didn't really preserve well, or we had contamination or something like that. So talk about being mad, but luckily I wasn't the one doing it. Okay, so don't trip over all these wires here. Okay, so in general, to look at the other redox active species, we really didn't see any correlation whatsoever. Okay, but there's definitely a strong relationship where when you have high arsenic, you have low sulfate and vice versa. And that was the same for uranium and partially molybdenum also, which makes perfect sense. Generally, even for uranium and all of these species, the oxidized species are the more mobile ones, and the reduced species are the less mobile, which is opposite to what you would expect for arsenic. So it seems to work fine. Okay, and the one thing that is clear is that in the basin, it's probably the change in the redox conditions going from the oxidized margins to the reducing basin that's controlling the mobility of our redox species. It's not all that clear for arsenic, if that's actually true. Okay, this is just looking at the arsenic 3, and since we've already seen that relationship before, I just want to re-emphasize what we're actually seeing here. And that's for molybdenum, uranium. Mn, this is the only plot I have here, but we really didn't see any correlation between Mn or iron 2. We don't see iron 2 increasing with arsenic 3 increasing. And so if we were going to argue for a reductive dissolution of the arsenic 5 sorbed onto iron hydroxide, if you have reduction releasing the sorbed arsenic or reducing it to arsenic 3, there isn't necessarily any correlation with seeing iron 2 increasing at the same time. Okay. So I'll quickly summarize this part here before we move on to the sulfur isotopes. I have a couple of minutes, I'll make this really quick. So no correlations were actually observed, statistical correlations, that is, but we do see a fairly sharp inverse relationship, not necessarily unexpected given the redox behavior of all of those species. Reductive dissolution seems to be consistent, however, no increase with dissolved arsenic, with dissolved iron. The one well that I talked about that had the highest arsenic is actually an oxidizing well that has arsenic 5. Okay, and that seems to contradict the earlier assumption that I was talking about in terms of the Fe hydroxide sequestration. I'm going to quickly move on to the sulfur isotopes. I think we're running out of time here. The take-home message from this year is in the basin. Remember, the pink squares are what's in the basin. The basin has a wide isotope ratio. Here again, I shall switch these axes, but they have a relatively wide range of isotope values going from fairly depleted to almost 36 per mil, which is fairly high. On the margins, sulfate is higher concentrations, but also a very narrow range. So we could assume that might be the background sulfate. Okay, we don't know that yet because we don't have the upgradient data, but that might really be the case. Now, explaining the heavier sulfur isotope data is relatively easy. Microbial mediated reduction, giving you enriched sulfate of what's left behind, makes sense. Explaining the depleted values, if we assume that is our typical range, then we run into a bit of a problem. Oxidation is one potential explanation for it. The relatively low concentration, so even if you had a small amount of oxidation, that would bias the ratios quite a bit. So that might be the case. When we talk of arsenic overall, okay, that just again basically echoes what we're seeing here, and it's going to be the opposite simply because where we have low sulfate, we have high arsenic, and vice versa there. And I have just 1 minute to sum up. So I'm not going to, I'll just quickly go to this last slide. So although there is evidence for sulfate sulfate reduction, we're not seeing lower arsenic. So the sulfate reduction forming sulfide is not taking out arsenic from solution, at least not to any appreciable extent. Definitely the one with high arsenic cannot be explained by oxidation of pyrite. It is an upgradient well. It is very possible that we have multiple redox zones, or that could be the actual sharp front between the oxidized zone and a much more reducing zone. We know it controls the arsenic speciation, but not necessarily its mobilization, which this part would then contradict the fact that the iron hydroxides would appreciably sorb high amounts of arsenic in this particular area. And I'll just leave the summary slide up for you and stop there. Thank you.
Unfortunately, we're out of time, so we have to move on to the next speaker. Yes, you walk away with it. And the speaker is Rick Wilkin, and the title is Arsenic Speciation in Groundwater, Role of Thionyl and Ions.
Right there. Okay, good. Thank you, Rudy. Okay, well, good morning, everybody. I wanted to spend a little bit of time talking about giving a status report on some of our work that we've been carrying out over a number of years, looking at the role of arsenic sulfur species in groundwater systems. I'm going to touch upon the results of some experimental and some field-based studies. Just first of all, a little bit of background. One of the reasons why we're especially interested in this particular topic is because that oftentimes at contaminated sites, remediation strategies are adopted that make some use of redox manipulation of the subsurface to achieve cleanup goals. And oftentimes, it's these sulfate-reducing environments that are the goal of these types of efforts. Now, arsenic may or may not be the focus of these types of cleanups, but it's very important for us to understand how arsenic behaves under these types of reducing conditions. And so what we have, of course, are sulfate-reducing bacteria that respire sulfate. They consume organic carbon, hydrogen sometimes. They can produce hydrogen sulfide, which can react with various reactive iron minerals to form iron monosulfides. And of course, there's a number of other side and very important processes that take place here. But the key thing to keep in mind is that depending on the overall rate of sulfate reduction and our overall supply of reactive iron, this is going to dictate how much free sulfide can build up in a system. And so this sulfide, if available, can potentially react with arsenate, with arsenite, and with arsenic sorbed onto mineral surfaces. And our questions here really have to do with what are the products of these types of reactions and what are the ultimate fate and transport characteristics of these reaction products. Now, ultimately here we're interested in the aqueous speciation of arsenic, but we can get some insight by looking at kind of the world of arsenic mineralogy. And ore deposits are especially rich in their different types of arsenic sulfur species that can occur. We can kind of group these into two different bunches: thioarsenites, where we have arsenic 3 coordinated with sulfur in the crystal structure, such as orpiment, which is perhaps the most common arsenic sulfide. Proustite, however, is a fairly important supply of silver in certain types of ore deposits. And then we also have thioarsenates. And here we have arsenic 5 coordinated with sulfur in the crystal structure, such as an enargite and its polymorph leucine. And these minerals in their own right can be fairly important sources of copper in certain types of deposits. And so the mineralogy tells us that there's at least a number of options that we might be looking at in terms of the aqueous speciation. Now, the tool that we've used here primarily, or at least one of the tools that we've used over the past several years, is X-ray absorption spectroscopy. We've already heard a little bit about that in this session. And we've made a number of significant developments here in looking at lower and lower concentrations. We can look at the 10 ppm to 50 ppm range in aqueous solutions. And in order to do this, we've used the insertion device at Sector 9 at the Advanced Photon Source at Argonne National Laboratory. In these experiments, we typically run in the flow mode at a flow rate of about 0.5 ml per minute. The cell volume here is about 1.5 milliliters, and that is placed directly within the fluorescence detector. All the samples, of course, are prepared in a nitrogen atmosphere, and we pump them through the flow cell under controlled conditions. And what we're going to look at are both the near-edge structure and also the extended fine structure portions of the absorption scans. I'm going to focus mainly on the Zane scans here as we go along. So where do we see these thioarsenites? First of all, we have a reference compound, orpiment, which has a well-defined white line position at about 11,870 eV. And you can compare that white line position to, for example, elemental arsenic, arsenic 3 coordinated with oxygen, arsenic 5 coordinated with sulfur, that's the thioarsenates, and also arsenic 5 coordinated with oxygen. And so where we see thioarsenites is after they form rapidly after mixing sodium bisulfite solutions with arsenite over the pH range from about 6 to 12. If you go to lower pH, you tend to form precipitates. Orpiment tends to precipitate out of the systems. And these thioarsenite solutions are stable over the duration of these scans, which can last 1 to 2 hours. In some cases, we've actually made up the solutions well in advance of coming to the beamline for the experiments. And here we've seen thioarsenites stable in solution for at least 2-week periods. Now, in terms of where we see thioarsenates, the literature on this particular topic and recently has been full of debate, interesting debate, and I think that's going to continue. Most of the literature here has been fairly polarizing in nature. That is, we either have thioarsenites or thioarsenates. Based on our work, we're beginning to see that really you can't discount either one of them. Both of these types of compounds form in these systems, and really the questions come down to what are the conditions that favor the formation of one or the other. Now for thioarsenites, here we have our reference compounds enargite and DMTA, which is a 2-to-1 thioarsenate. And you'll notice the white line position for these compounds is about 11,872 eV, and that overlaps very closely with the white line position for arsenic 3 coordinated with oxygen. And this generally hasn't been recognized, and the implication is here, based on Zane's data, you really can't tell the difference between a thioarsenate and if you have arsenic 3 coordinated with oxygen. You can get some information by looking at the extended fine structure or other types of information, but just based on the Zane's data, you really can't tell. So if we look at some of these experiments, if you look at the kind of the equivalent experiment of taking arsenate and exposing that to a sulfitic solution, at least over short periods of time, you really don't see any change. Arsenate remains arsenate. You allow that solution to age for here 3 weeks, and you begin to see the decay of the arsenate peak, and we begin to see thioarsenates form. So one pathway to forming thioarsenates is slow reaction of arsenate with bisulfite. We've also seen thioarsenates in this alkaline synthesis procedure of Schwett and Wycroft that does indeed form thioarsenate salts. And interestingly, we've seen thioarsenates form as we dissolve realgar in fairly concentrated sulfide solutions. Now, importantly here, thioarsenates are destroyed in the presence of sulfide at low pH. They react to form thioarsenites and ultimately orpiment if the conditions are right. So one of the other tools, the other major tool that we have for looking at arsenic speciation in solutions is the chromatography method, HPLC ICP-MS, and here we're using a sodium hydroxide gradient elution method. This method is not sensitive to the oxidation state of arsenic, so both thioarsenites and arsenates co-elute, but it's very sensitive to the concentration of arsenic. And so one of the types of experiments that we conduct are what we'll call stability experiments. Here we make up a solution with constant pH, sulfide, and arsenic, and we allow that solution to age through time and look at traces. And what we typically find is that we rapidly reach some a steady state, and we don't see a whole lot of change after that as long as we keep conditions constant. The other type of experiment that is quite useful is what we call a sulfide titration experiment. Here we're going to keep the pH constant, arsenic concentration constant, and we're going to add in incremental amounts of sulfide. And here we'll look at the changeover from where we have dominantly oxyanion species to where we have dominantly thioarsenic types of species. So if we put a number of the results from these types of experiments together using different pH buffers, you see that you get a trend here, or a measured a determination of where you have oxyanion-dominated solutions and where you have thioarsenic-dominated solutions. And this blue line is our measured line here, and it compares fairly well with predictions from data we published a number of years ago. And this type of information is now quite useful for looking at and comparing with data that we collect in the field. And as I mentioned earlier, we're particularly interested in these sites where some sort of in situ redox manipulation takes place to achieve some sort of groundwater cleanup. I'm going to use an example or several examples from sites where we're using the permeable reactive barrier technology. One site is the East Helena site in Montana. And here we have a pilot-scale granular zero-valent iron system that was installed to test the technology for dealing with arsenic in groundwater. The other site that I'm going to talk about a little bit is the Delot metal site. And here, the reactive mixture is a cow manure plus limestone. And this system was put in place to deal with lead, cadmium, and low pH. And note that arsenic, at least initially here, was not something that was being dealt with in terms of a site cleanup effort. Okay, so these are some data here from the East Helena site. Here we're looking at arsenic or sulfite concentrations versus pH within the PRB over about a 2-year time period. And you see here that sulfite concentrations really never get to a level such that we would push into this field of where thioarsenics dominate. And that's primarily because we have a lot of reactive iron in the surface, and so sulfite concentrations simply aren't able to build up. Now, as we look at points that are close to this line, we do in fact see that we have some of these thioarsenic compounds. They are forming in the system, but at much lower levels than we might otherwise expect, because of all this reactive iron being present. Now, what's important here is when we look at the solid phase partitioning of arsenic, and this is looking at Zane's analyses of cores collected from the reactive media. What we see here is very interesting. We have multiple oxidation states, multiple bonding environments for arsenic within the reactive media. This is much different from what you see when you just do simple column tests with zero-valent iron, where you typically just see one condition forming in a particular system. These field environments, we're getting multiple oxidation states, bonding environments, suggesting really multiple uptake processes. And importantly, based on the linear combination fits of the Zane's data, we see anywhere from about 25 to 75% of the total arsenic being tied up and associated with sulfur. And so clearly this interaction between arsenic and sulfur is an important uptake process within this reactive medium. Now the Delot site is a little bit different. Here we have a lot of organic carbon in the PRB. We have a lot of sulfate, but we're limited in the amount of reactive iron or other reactive metal at the site. And so sulfite concentrations here are able to build up to fairly high levels, up to about a millimolar concentration. And here we expect to see the accumulation of these thioarsenites in solution. And in fact, as you increase the molar sulfide to arsenic ratio, we do see, this is based on chromatography now, an increasing amount of the arsenic fraction in solution that's present as these thioarsenic species. Now, what's important here is that at this particular site, we see we don't have a lot of arsenic upgrading to the PRB, but because of these reducing conditions that we've created within the PRB, we're actually forming a mobilized arsenic plume that's moving down gradient. So this is not a particularly good thing for this particular cleanup effort. All right, so the current status here in this work is that thioarsenic species predictably form in subsurface reducing environments. And there are clearly implications here regarding these strategies that rely on redox manipulation in groundwater systems. We're continuing to look at that. Both thioarsenates and thioarsenates need to be considered. I don't think at this point neither one of them can be discounted in terms of our assessments at field sites. Analytical methods, these have their pros and cons. The Zane's, or X-ray absorption technique, is certainly very powerful in terms of its ability to determine oxidation states. It's not especially sensitive. It's not especially practical, especially for our routine work at field sites. The chromatography method is more suitable for doing field studies, of course, except we're not getting this oxidation state information that we'd like to get, but it is especially sensitive to concentration. A couple other issues here regarding preservation. I noted earlier that acidification is a real problem. You can't use our common technique of preserving samples, that is acidification, because that tends to destroy these types of species. And so we have to look at other types of methods for preserving samples, such as freezing. And currently some work is looking at manipulating samples prior to the chromatography to try to get a better handle on the speciation using some of these manipulations pre-chromatography. So with that, I've got a couple of acknowledgments here of some groups and individuals that have been helpful here, but I think we should have time for questions, and I appreciate your attention. Right.
Do you have an idea of how far down gradient that process is?
It's interesting. A lot, unfortunately, this observation of arsenic being mobilized from these types of systems has been seen before when it's looked for. And oftentimes the explanation is, well, eventually we're going to come back to some background condition and the arsenic will drop off, usually related to iron as well. But here at this site, I don't know if you noticed on the map, there's actually a surface water body that was really abutted very close to the PRB, and so we expect that there's actually discharge of that arsenic into that small creek there. And that, I mean, when the PRB was put in place, this was not something that they were looking for, and really EPA is kind of slow to see a problem like this and to figure out what to do once something like this comes up. And so there hasn't been a lot of monitoring to understand how much discharge there actually might be.
Other questions?
Robert.
Do you think there's anything gained with the work that's happened in the past to make oxidation state of arsenic in untitled species where the reduced forms were quite low in terms of the chromatography options that they give?
Oh, that may be, and that's, I think, how they've been able to deal with some of that, right? In terms of, because most of what they're seeing is the arsenic 5 methylated species. And so I think some of those manipulations may be useful here in terms of preserving either the arsenic 3 or arsenic 5 sulfur forms. I think that's a good idea. Thank you.
Thank you. Our next talk will be given by Patrick Longmire, and we'll be hearing about a whole new element. We'll be hearing about chromium.
Chromium.
It's very exciting.
Okay, thank you, Alice.
You can,
And then to advance it.
to advance it, theoretically, you can just use the mouse, although people seem to be having problems.
Okay, so we're going to shift from element number 75 down to 52, chromium. And at Los Alamos, from the period of 1956 to 1971, between 31,000 and 72,000 kilograms of potassium dichromate were released from a cooling tower, and it dissociated to form chromate under the alkaline pH conditions, and then migrated down about 1,000 feet to our regional aquifer. So this probably, in my opinion, represents the most significant groundwater problem at the lab in its entire history. Okay, so the purpose of the presentation is to present an overview of the geochemical processes influencing the distribution and reactivity of chromium in the subsurface at Los Alamos. And the topics of interest include quantifying the speciation, adsorption, precipitation of chromium-3, chromium-6, evaluating freq-C results for experimental studies, and looking at some chromium-stable isotopes, chromium delta-52. Let's see, in the mount or the laser pointer. Oh, here we go. Okay, so this represents the main source of chromium for the laboratory, and this is a view of the Rio Plateau with the Jemez Mountains to the west, groundwater flow in the regional aquifers to the southeast. And here just shows we're working with unsaturated, saturated flow, porous media flow, and fracture flow, and very complicated system hydrologically. And so we have the Bandelier Tuff, the upper left portion here, the Cerros del Rio basalt, which can be important, especially with the ferrous iron minerals. And then at the regional water table, the PHUC formation, the Santa Fe group formation. And here just shows some of the typical reactive solids. And our groundwater is oxidizing. We measure dissolved oxygen, and the redox couples are probably controlled between dissolved oxygen and water, manganese 4 plus, manganese 2 plus. And here shows a table of our median groundwater composition in millimoles per liter, milligrams per liter. Basically a calcium-sodium bicarbonate solution with the chromium concentrations about 5.8 times 10 to the minus 5 millimoles per liter, or about 3 micrograms per liter. And as we did the speciation with ion chromatography, all that natural chromium is chromium 6 plus, which was interesting. Okay, here's a map of the central portion of the laboratory, the regional aquifer wells. Background chromium is between 3 and 6 micrograms per liter of parts per billion. Our contamination ranges from about 800 to 1,000 micrograms per liter in the regional aquifer, which is at a depth of about 1,000 feet. Okay, let's just review some of the oxidation reduction chemistry of chromium. Under oxidizing conditions, we have bichromate, chromate stable. Under relatively reducing chromium reducing conditions, chromium 3 plus, and then a series of hydrolysis species form. And within the lannel groundwaters for the regional aquifer perched intermediate zones, generally oxidizing. And R28, regional well 28, is oxidizing, where most of the chromium, the 400 parts per billion chromium, is stable as hexavalent chromium at a pH near 8. Now, in the perched intermediate zones, the Cerros del Rio basalt with the ferrous iron can be slightly more reducing, and there is the potential for reduction of hexavalent chromium to chromium 3 plus. And under reducing conditions, this blue box area defines the stability field for amorphous chromium hydroxide drawn at a concentration of about 0.5 ppm. And so in natural systems for chromium oxidation, there's been a lot of work showing the importance of manganese dioxide, manganite, and so I have these redox reactions written here. And then for chromium reduction, ferrous iron containing minerals, and in our system, olivine may be important in the basalts, dissolved iron 2 plus, dissolved in solid organic carbon. Okay, so we drilled core samples, and these are some data for the unsaturated zone, where we did a series of leaching with deionized water, analyzed the chromium by ICP mass spec, corrected it for the pore water concentration, and then performed a 30-50 digestion with nitric acid that partially dissolves some of the oxides, and took the ratio of the 30-50 digested chromium to the deionized water to calculate an apparent distribution coefficients. And I want to stress that this method doesn't give us the resolution for adsorption versus co-precipitation. It is just an apparent experimental parameter. So here's a plot of our KD in liters per kilogram versus weight percent iron, and perhaps true adsorption of chromate onto ferric oxyhydroxide may occur at lower KD values, but this may represent a precipitation process, and I have the different hydrostratigraphic units defined here, and then in the basalts, TCB, having higher values, which could be certainly related to the reduction of chromate to chromium 3+. So there is some residual chromium within the vadose zone that's an important source term to look at, so that potentially may migrate to the regional water table. Now, May and I did a series of adsorption experiments, batch experiments, and these show the histograms here. And we took samples that were not crushed, and looking at less than 75 micrometers up to 2,000 micrometers, and then we had crush samples. And most definitely with the crush samples, we had higher apparent distribution coefficients approaching 1,000. And this, our hypothesis is that this is related to a reduction. And May had performed some XFS experiments, and indeed it does support the reduction precipitation of chromium hydroxide. For the samples that were original, that weren't altered, the KDs are less than 10. And this kind of compares favorably with our apparent KDs that we had calculated using the DI leach and the 3050 partial digestion. That is ranging typically between 10 and 1,000. Okay, we've conducted some column experiments. We're interested in the reactivity in many of the media, and this shows a breakthrough curve of pore volume versus C over C naught. C naught, the initial concentration, C, the concentration is a function of time. We introduced a tracer lithium bromide and see a nice breakthrough for the bromide. And then we introduced in chromate at a concentration of about 6.7 parts per million, or a log molality of minus 3.89. And all our chromium concentrations were less than detection using ICP mass spec, so less than a tenth of a part per billion. So in this one column with the basalts, there certainly could have been the reduction of chromate to chromium 3+. And so I attempted to model our column results using PHUC. And when you model, it's good to have multiple hypotheses. This is just one reaction. Working out the stoichiometries of our weight percent of olivine and identifying ferric hydroxide, ferrous carbonate in the system, modeling this reaction, and constraining it with the influent concentration, setting the code in equilibrium with chromium hydroxide, determining the time step based on our pore volumes, and using a flux-flux boundary condition, and assuming a dispersivity of 0.002. What's important is that the concentrations of the effluent coming out of the column predicted by PHUC were right in line with our analytical results. That is less than detection. So that's just precipitation. Now, I did another simulation assuming that there would be potential adsorption of chromium 3+ on hydrospheric oxide, HFO, at a millimole concentration, and what this had predicted that there would be much less concentrations of the chromate, or chromium 3+, adsorbed onto the ferric hydroxide. So adsorption really wasn't that important in these column experiments. We're going from about 6.8 ppm down to less than a part per billion, a concentration of chromium in the effluent. Okay, one other aspect that Jeff Hycoop and I are looking at are chromium isotopes. And with this, as chromate gets reduced to chromium 3+, it's the chromium 52 that's involved in that reduction reaction, and the residual chromate becomes enriched in the chromium 53. So the delta 53 value becomes more positive. So here is a plot of the fraction of chromium reduced with the fractionation lines here versus delta 53 chromium per mil. And what we see is our basalts that have the ferrous iron concentrated tend to show the most consistent higher values of delta 53 chromium, again supporting the reduction of chromate to chromium 3+. Surface waters, the PHUC formation without a lot of iron 2+ minerals, very little potential for reduction. So we don't see that much enrichment at all in the delta 53 chromium values. Now here is a plot of delta chromium 53 per mil versus the concentration of organic carbon and milligrams carbon per liter, and the suspended iron in micrograms per liter. And if iron 2+ is the electron donor, it's reducing the chromate to chromium 3+, then iron 2+ gets oxidized to iron 3+, should precipitate from solution at these alkaline pH values, and we see a pretty good correlation with the increasing heavier values for delta chromium 53 versus our suspended iron. And the p-value for this, if you believe the statistics with this, is that 999 times out of 1,000 there would be a significant correlation with this suspended iron and enrichment of the chromium 53. Okay, conclusions. The two oxidation states of chromium differ in their toxicity, mobility, and reactivity in natural systems. Second point is, at Los Alamos, the Vado zone and the regional aquifer materials show different adsorption precipitation capacities for chromium 3+, chromium 6+, reflecting a large variation in our apparent KD values. And higher KD values tended to be associated with the crush samples, reduced particle sizes, which is a surface area phenomena, and just having more exposed minerals, such as olivine with iron 2+, making it much more reactive. And precipitation of chromium hydroxide under relatively reducing conditions within the iron 2+ aquifers is supported by our experimental results, the chromium isotope signatures, and even by calculations using PHUC. Thank you.
We do have a minute for a question or two.
Yes.
Sorry.
Okay.
The gentleman all the way back.
Okay.
Sir.
Yes. Okay, the question is, I showed a plot of, for unsaturated core, apparent distribution coefficients, and with varying moisture content. They do have varying moisture content, and that is different than the groundwater. And that's a real good question that could influence the apparent KD value. We do back correct for our pore water concentration by knowing the moisture content, the mass of the sample, etc. Now, in the groundwater, I think with the pH and also, having more dilute solutions. For example, we had several samples in the unsaturated zone where the pore water chromium concentration exceeded a milligram per liter. And so just having it more concentrated, and having it unsaturated, I think that does tend to increase the concentration, at least in some samples. Thank you. Yes?
Yeah, I want to follow up, and correct me if I heard it incorrectly. I think I heard that you had the capability of doing speciation of chromium in solution, and that there were some measurements of chromium oxidation state in solids. With any of the extractions of your solids, have you done solution-based speciation measurements to see if there's some correlation and if you rely more so on the extraction data?
No, we basically, for our extraction experiments, relied on the amount of total dissolved chromium. But for the solids in our batch experiments, column experiments, we have done the XAFs, and that does, support the reduction of chromate to form chromium hydroxide. Okay, thank you very much.
Our last speaker today will be Siddhartha Bhattacharya, and he will be taking us back to arsenic, I believe.
Okay, so good afternoon. The topic of my today's talk will be the chemical fixation of trace elements in coal fly ash using the ferrous sulfate treatment. So we know that 50% of the electricity that is generated in the US comes from coal-fired electric power plants, and it produces large volumes of coal combustion products, and of which only 40% is actually reused. So like fly ash constitutes about 60% of the coal combustion products, and it contains high concentration of hazardous leachable trace elements such as arsenic, boron, chromium, nickel, selenium, strontium, and vanadium, and they have a negative impact on the environment because of the potential leaching by acid rain or groundwater. So because of the presence of these trace elements in fly ash, like we face challenges in the coal combustion product disposal site management, and also it limits the beneficial use of fly ash. So because of the presence of these toxic trace elements, we need a simple and effective in situ treatment technique which will stabilize the trace elements in coal fly ash. Several chemicals have been actually used in the in situ chemical fixation studies done earlier, and those chemicals are like calcium aluminates, phosphoric acid, some surfactants, sodium hydroxide, and also chemicals like ferric chloride, which have like iron-rich solutions, which will precipitate ferric hydroxide into the fly ash. And one of my former lab members actually successfully applied the ferrous sulfate treatment to treat a soil sample contaminated with arsenic trioxide by the formation of insoluble ferric oxyhydroxide on the soil particles. So the objective of my study is to chemically fix the trace elements in coal fly ash using ferrous sulfate treatment. So I'm going to show you the results of the bench scale lab experiments that was performed to study the long-term immobilization of these trace elements in the treated fly ash. And also we want to know the mechanism by which the ferrous sulfate treatment actually works by using a 7-step sequential chemical extraction procedure. So we know that the mobility of trace elements in coal fly ash actually depends mainly on the composition of the feed coal, but it also depends on the age of the fly ash already disposed in the disposal facilities, and also environmental conditions such as EH and pH. So based on that, we selected 4 fly ash samples. All these 4 fly ash samples are actually coming from power plants that are located in the southeastern United States. And 3 of those samples are actually acidic, derived from the eastern bituminous coal. And I selected one alkaline fly ash sample, which is derived from the Powder River Basin coal. This slide shows the chemical composition of the 4 different fly ash samples that I collected. The HA, HB, and MA, please remember that these are the 3 acidic fly ash samples, and the PD is the alkaline fly ash. We used the microwave-assisted nitric acid extraction digestion technique to find the chemistry of the fly ash. As we can see that the acidic fly ash is dominated by aluminum and iron, while the alkaline fly ash is dominated by calcium, and the concentration of other major and minor trace elements such as magnesium, potassium, sodium, and strontium are similar among the 4 fly ash samples. Now, if we look at the trace element concentration, we see a very high concentration of boron in the alkaline fly ash, which is more than 900 parts per million dry weight. But if, with the exception of boron, all the other trace elements are actually like the three acidic fly ash samples are actually have higher trace element content other than boron. So now I'm going to talk about the different ferrous sulfate treatment experiments that I performed. In the first set of experiments, I used an unbuffered ferrous sulfate solution having iron concentration of 322 to treat the fly ash at two different solid liquid ratios of 1:3 and 1:30. Then in the next set of experiments, I buffered the same ferrous sulfate treatment solution. What I did was I used the same ferrous sulfate solution, but I added 1.5 gram of solid calcium carbonate to actually buffer the treatment solution so that we have a abundance of hydroxyl ions in the treatment solution, and I thought that it will facilitate the precipitation of ferric hydroxide. So after the treatment was actually done for 7 days, and then after the treatment was over, we collected the supernatant treatment solutions and then separated the treated fly ash from the solution and air dried it for 7 days for further experiments. Now, to study the effectiveness of the treatment, we actually used a sequential leaching of the treated and untreated fly ash using a synthetic acid rain solution. And this synthetic acid rain solution is nothing but a very dilute mixture of nitric acid and sulfuric acid. We used a 22-hour leaching cycle, and we continued the leaching for 40 days. And after the leaching was over, we compared the amount of trace elements that were released from the treated as well as the untreated fly ash samples. Now, this plot shows the amount of ferric hydroxide that has been added to the fly ash particles after the treatment was over. Now, I can justify that by actually buffering the ferrous sulfate treatment solution, we have actually managed to increase the amount of ferric hydroxide precipitated. By the way, in this calculation, I actually assumed that all the iron that has been removed from the treatment solution has actually formed the ferric hydroxide. Now, I'm going to talk about the trace element mobility during treatment. If you remember, I collected the supernatant treatment solution after the treatment was over, and in this slide, I'm showing the oxyanionic trace elements of interest, whether they're released during the treatment or not. As you can see, a maximum of 0.6% of arsenic, a maximum of 2.8% of chromium, and less than 2% of vanadium was actually mobilized during treatment. Now, in case of molybdenum, you can see here that the unbuffered treatment solution actually do not release any molybdenum during treatment, but the buffered, especially the buffered treatment, ferrous sulfate treatment at 1:3 ratio, removed significant amounts of molybdenum during treatment. And also for selenium, we see very little selenium mobilized during treatment by the buffered solution, but it actually mobilized almost 15% of selenium the unbuffered treatment solutions did not release any selenium during treatment, but the buffered treatment solutions actually released up to 15% of selenium. Now, these are all the oxyanionic trace elements of interest. Now, if we look at the other trace elements, we can see from the first plot here that significant amounts of boron has been mobilized during treatment. And if you look at strontium, we can see that for the HA and MA fly ash, which are both acidic, we release up to 36% of strontium during treatment. But if you look at the HB fly ash, which is acidic, and the PD fly ash, which is alkaline, the 1:3, it doesn't matter whether it's buffered or unbuffered, the 1:3 treatment solutions released absolutely no strontium during treatment, but it's the 1:30 treatment ratio which released up to 44% of strontium from these two fly ash. Now, up to like a maximum of 8% of nickel is actually released by all these treatment solutions during treatment from the acidic fly ash, and absolutely no nickel was released from the alkaline fly ash during treatment. In this slide, I'm going to talk about the summary of the treatment results that I have, on the results that I got from my treatment experiments. If you look at the figures on the y-axis, I have shown the percent mobility reduction. What I did was I actually compared the amount of trace elements which are released from the treated fly ash samples, and then compared it with the untreated. And any trace element that has been released during treatment has also been accounted for in this calculation. So if you look at the arsenic plot and also the selenium plot, you can say that the unbuffered ferrous sulfate treatment at the 1:30 ratio is actually most effective for the oxyanionic trace elements. And you can see that it has reduced the mobilities of these oxyanionic trace elements by significant amounts. And if you look at, and also if you look at this plot, you can both of these plots, you can say that we actually increase the mobility of these oxyanionic trace elements by the buffered ferrous sulfate treatment at the ratio of 1:3. And if you look at the alkaline fly ash, you can see that all the treatment solutions actually manage to reduce the mobility of all these oxyanionic trace elements. Now, if we have seen the results for the oxyanions. Now, let's look at some other trace elements. Now, if you look at the results of boron, you can see that in the 3 acidic fly ash samples, all the treatment solution actually increased the mobility of boron. But for the alkaline fly ash, you can see that the unbuffered solution as well as the buffered solution at the 1:3 ratio managed to decrease the mobility of boron by a few percentages. Now, if you consider the unbuffered 1:30 ferrous sulfate treatment as the most successful for the oxyanions, you can see that it has actually increased the mobilities of all these of the uncharged boron and also the cations of nickel and strontium by significant amounts. And also, if you look at this plot for the nickel plot, you can see that the 1:3, it should be the buffered. So 1:3 buffered ferrous sulfate solution actually, which was unsuccessful for the oxyanionic trace elements, was actually successful in reducing the mobility of nickel. And for the alkaline fly ash, you can see that the mobility of nickel was increased by all the treatment solutions that we used. And although I don't have the plot here, but for the strontium in the alkaline fly ash, all the treatment solutions actually reduce the mobility of strontium. So now quickly look at some plots here where we used a 7-step sequential chemical extraction procedure to know about the mechanism by which the ferrous sulfate treatment actually works. Here what we did was we extracted 7 fractions of trace elements in the fly ash, in the treated and the untreated fly ash. Now you can notice that I have not actually performed this 7-step extraction procedure on the buffer treated fly ash samples because I consider that not very effective for the oxyanions. Now if you look at arsenic for the HA fly ash, which is an acidic fly ash, you can easily see that we have actually managed to transfer the water soluble, exchangeable and the acid soluble fractions of arsenic into the more stable, easily reducible, moderately reducible and poorly reducible fractions in the treated fly ash. Now these 3 fractions are actually highly mobile in the environment, and the target fraction for the ferrous sulfate treatment is actually the moderately reducible fraction, which is right here, which is actually the amorphous iron oxide or hydroxide fraction. So this plot tells you the mechanism by which arsenic is treated by the ferrous sulfate treatment. Now we know that boron, like the ferrous sulfate treatment solution, has actually mobilized boron in the fly ash samples, and I give you one example where you can see that in the untreated HA fly ash, which is acidic, you have significant amounts of water soluble boron which is released during treatment, and that boron is actually remains mobile and it's released into the environment. So because of this very high concentration of boron in the water soluble fraction, we see that boron has been mobilized during treatment. So finally, we can conclude that the ferrous sulfate treatment actually promotes the formation of insoluble ferric oxyhydroxide phases, which immobilize the trace elements. And these oxyhydroxide phases are very insoluble. And the most effective treatment in this study is the unbuffered ferrous sulfate treatment solution at the ratio of 1:30. It reduced the mobilities of the oxyanions, but it actually increased the mobility of the cationic nickel and strontium, as well as the uncharged boron from mainly the acidic fly ash samples. Some other conclusions: ferrous sulfate treatment will not be suitable for reducing environments because the ferric hydroxide will be in reducing environments, it will be dissolved, and it has the potential to release the trace elements that are in the fly ash. But most of the time, almost in all cases, the fly ash disposal facilities are always built above the water table, so we normally expect an oxidizing environment. And also it will be very cost effective. We can directly apply this ferrous sulfur treatment in the power plants which is producing fly ash every day, and can also be applied to the fly ash which is already disposed in the fly ash disposal facilities by the method of injection. Now, I did some cost studies, like just to give you an understanding how cost effective it is. Like for a power plant which is producing 500 megawatts of electricity, if we treat all the fly ash produced in the power plant like this, we'll incur a cost of about 1.89 million. And I talked with the PowerPoint officials, and they said that this is a cost-effective figure. So just an idea for you. So finally, some acknowledgements. I'm particularly thankful to Dan Patel for his help in the research, the EPRI for funding, Betsy Graham for analysis of the samples, and also my some former and current lab members. So thank you, and if you have any questions.
We have time for maybe one question before we break for lunch.
Yes. The fly ash is pretty homogeneous, but we tried to make sure that, like, we collected a bucket, like a 30-gallon bucket of fly ash, and we tried to mix it properly. But there is, like, I have observed some heterogeneity in the fly ash as well. So I'm not going to say that this fly ash was very homogeneous, but it's pretty homogeneous, like, if that answers your question. So.
Thank you all so much for your attention and for attending.